Please pause the video and take a moment to read this important safety message.
All right, hopefully a fun and educational video here at Blue Glow Electronics today. First, we're going to do a little bit of education on what coupling caps are, why we might need to replace them, and then we're going to dive over on the bench and show you actually how to replace a few of those. All right, let me start by saying I believe that capacitors are one of the most misunderstood and possibly complex devices that you will use in electronics. And the reason that is they serve many purposes in an electronic circuit. So unlike a resistor, which typically serves a single purpose or a very few purposes, capacitors seem to get used in a lot of different ways to do a lot of different things in a circuit. You can see here in the top right hand corner, I've drawn out here a sine wave or an alternating current signal. Okay, so an AC signal. And if we'll notice here, one of the things it mentions that capacitors block DC but allow AC signals to pass through them. So in other words, you look at this second picture here. So if we had a single wire that on that wire had, let's say, 100 volts of DC, but a 5 volt signal of AC, both happening on that same wire, and you happen to feed that through a capacitor, what will happen is the DC will get blocked, and on the other side of this capacitor, you will have 0 volts of DC, and you will have your 5 volts of AC on the other side of this signal. So we use capacitors to do something called coupling between stages, or some may even call it decoupling between stages, because we're kind of decoupling the DC components as we move between various stages of an electronic schematic. If you'll notice here, I said when AC and DC are present at the same wire at the same point in time, they add together, resulting in an AC signal that has a DC offset to it. So a 5 volt AC signal being offset by 100 volts of DC, okay? And we use coupling caps to keep this offset DC voltage from making it to the next stage, all right? Another interesting little thing here, coupling caps are typically non-polarized, meaning they have no positive and negative terminals to them, and it really doesn't matter which way you install them. I'll throw out a caveat here. There is an outer foil approach that would say that maybe one side of the capacitor would be better to hook up than the other to the positive or negative, but that's a minute thing, and we're not going to talk about that today. For all intents and purposes today, coupling caps are non-polarized. And if we look at how they make these capacitors, it's typically just a thin layer of metal foil wrapped up within a dielectric material, either polypropylene, polyester. Back in the old days, it used to just be some paper that was soaked in wax. And then what happens is this gets rolled up and looks like this picture down here, and then they typically coat the outside of it with some type of insulating material to seal up the package. And what happens over time is the chemicals inside of these that are used start to break down, especially the old wax paper type. In other cases, the metal foil and kind of plastic that are wrapped up together start to disform because they draw moisture or heat or whatnot. And these capacitors start to break down over time. And once you get a layer of a capacitor to kind of start breaking down and you get a little burn through to the next layer, it's kind of a self-perpetuating failure at that point in time. In other words, it starts to disintegrate pretty quickly. So the reality is these older coupling caps are likely going bad or starting to exhibit characteristics that aren't as good as when they were new, and thus we need to replace them. And it's kind of easy to tell, to be honest, and I'll show you here in just a second. All right, let's just take a look at a basic schematic here I borrowed offline. It's just a 6M1P driving a KT88, which might be familiar. But let's take a look over here. We've got a little bitty teeny audio signal coming into this unit. It's coming over here. It's being amplified by the 6M1P. It's riding up here on top at this point, coming off the plate, and it's starting to feed through this coupling capacitor to go on to the next stage and feed into this KT88. Well, if you'll notice here on the plate of this 6M1P, we've got 400 volts sitting right here. So what you'll have is this little signal that's been amplified here being offset by the DC of 400 volts. Well, the 400 volts on the plate of this 6M1P is great. It's exactly what we want. However, this signal flowing over here going to the next tube here, the grid of the KT88, you do not want 400 volts sitting on the grid of your KT88. You likely want something closer to 0 volts. So what do? We insert this little capacitor right here to let the AC signal flow through and get amplified, ultimately come out of the plate of the KT88, go through the output transformer, and drive your speaker as a much larger signal over here, okay? But if it wasn't for this little coupling capacitor right here, that's actually kind of decoupling, actually, the DC between these stages, you would have 400 volts sitting right here on the grid of your KT88, which is going to light it up red like a Christmas tree and burn your tube up very quickly. So we use a coupling cap here. And what I said here, as these devices age, their physical chemical attributes change and break down, resulting in caps that leak and allow some DC to pass through them. So what do you mean by that, Mark? All right, well, what if we took a DC voltmeter and we connected the black lead down here to ground, and we connected the positive lead up here at the plate of the 6M1P? We would measure 400 volts, right? Well, then what happens if we take the red lead and we move it over here to the other side of this coupling capacitor? We would expect to see something closer to 0 volts over here. But what if instead of that we saw 70 volts or 100 volts or 40 volts? In other words, what's happening is this capacitor is starting to break down and leak and letting some of that voltage come through to the other side. And if it's enough voltage, it'll play with the bias of this next stage and really throw things all out of whack. And that's typically what happens. You can actually measure these units in circuit and just measure on one side and you'll see 400 volts, measure on the other side, and maybe you only see 14 volts. But that 14 volts is 14 volts too many. And it shows that that capacitor is starting to break down and you really need to replace it. If you don't, you run the risk over time of it continuing to break down, continuing to increase how much DC it leaks through, ultimately kind of frying this tube right here and causing you all kinds of problems with your amplifier. All right, let's talk about our approach a little bit. First approach would be to find an exact replacement value-wise. So in that previous schematic, if you'll remember, that was a 0.22 microfarad capacitor at 600 volts. We should go in and replace that with a 0.22 microfarad capacitor at 600 volts, okay? Find a newly manufactured capacitor that matches the existing capacitor microfarad-wise. You can do that. All right, second up, I've seen this in forum posts a lot. Hey, what if I change that 0.22 microfarad to a 0.47? Will that help me? Well, this is not the same as a capacitor used in a power supply where you're creating an energy reserve. This is a capacitor coupling stages in your amplifier where that capacitor is actually acting as a low-pass filter. A high-pass filter, and you're really not wanting to change that value. There may be implications, and we'll talk about that on the next slide. So higher value is not necessarily better as it comes to coupling capacitors. And then the last one you could do is find a new old stock replacement. Ooh, I'm going to go find me an old Bumblebee capacitor, just like the one that was in my amplifier, and I'm going to replace it with that. Highly not recommended. These old capacitors, they start leaking whether they're being used or whether they're not being used, and so likely just to lead you down a road of problems. And then I've got the big statement here in blue. Regardless of the approach, it is recommended that the replacement coupling cap be at least the same value or greater voltage-wise. Never replace a 400 volt cap with a 250 volt cap as an example. It's always okay to replace a 400 volt cap with a 600 volt cap, as long as it doesn't get too large physically to fit where you need to install it. I see guys sometimes that go online and they'll buy Russian paper and oil caps, and they're like, oh man, I need some 0.33 microfarad capacitors, and they're sold out of the 400 volts and they're sold out of the 600 volts, but they've got some 1000 volts. Let me order those. And they get them in, and they don't realize that these things then are, getting pretty good in size, about the size of a 12AX7 tube at that point. And they're like, holy cow, I don't have enough room to fit all these in my amplifier. So pay attention to as you go up in voltage, the physical attributes of a capacitor get larger, thus the overall size of it gets larger. Okay, if we want to talk about changing the value of a coupling cap, the first thing you've got to understand is this coupling cap joined with the resistance or impedance of the following stage work together to form what is called a high-pass filter. In other words, it lets higher frequencies flow through here, and it sends frequencies closer to 0 hertz or DC, sends those frequencies off to ground here. Okay, that's the way this CR filter works. And that can kind of be measured by a -3 dB point on a frequency plot. But the bottom line here is frequencies above this are getting sent on through, and frequencies down here in the lower region, maybe 0 hertz, 10 hertz, 20 hertz, are being sent to ground. And the way you figure out this frequency cutoff point is FC is equal to 1 over 2 pi RC, which you guys don't need to understand this stuff. I guess my point in showing you all this is, if you want to get into changing the values of coupling caps and potentially changing the tone of your circuit, you would need to get into this type of mathematics and start to understand what frequencies are you trying to cut off and which frequencies are you trying to allow through. And that's why we're not going to get into that. The bottom line here is I'm saying we need to stay as close to the original manufacturer design microfarad wise as possible. So that's not always practical though. And I'll give you an example here. If you're replacing a 0.5, which was a not so common value today, but was years ago, 0.5 microfarad capacitor with a 0.47, which is pretty darn close to 0.5, which is a common value today, you are probably okay. In other words, you would not change this frequency cutoff very much at all. If you were to change the value any, so if you did, let's say you didn't have a 0.47 and all you had was a 0.68, and you said, well, I wonder if I could use this 0.68 instead of this 0.5. I would recommend you conduct a frequency response sweep of your circuit. If you want to know how to do that, I've made some videos on the Analog Discovery 2 setup. But you would need to do a frequency sweep and make sure you're not starting to drop off too much on the bottom end, frequency-wise. And I made an interesting note here. Some amp designers choose coupling cap values to intentionally roll off AC below 50 hertz or so as part of their design. In other words, in their mind, they're saying, look, this amplifier circuit here really doesn't need to amplify 20 hertz, so I'm going to roll that off and not waste that energy in the circuit. And I'm going to send everything above 50 hertz or whatever on through to the next stage. So, you just got to be careful in changing these values, because sometimes people chose values for a very specific reason as part of their circuit design. So my recommendation, stay as close to the original manufacturer's design as possible. And if you're not going to do that and you're going to play around, you need to check the frequency response to make sure you're not hurting your circuit in some way, shape, or form response-wise. So you say, okay, Mark, you've convinced me I need to change my coupling capacitors in this old vintage gear. What should I use? Well, here are some common examples of what gets used very frequently by electronic restoration technicians all across the world. So first and foremost up here, the Mallory 150M series yellow poly caps. And they don't have to be necessarily Mallory branded. They could be a knockoff of Mallory or whatnot. But they typically look like these yellow ones right here. You can see this is a 0.47 at 630 volts. The beauty is they come rated at 630 volts. They're fairly small size. They're very reliable, and they're very inexpensive. And, it's not a bad choice to go down that route whatsoever. Up next, Sprague orange drops. 715P series or 716Ps. They're easily found in common values, and they come rated at either 400 or 600 volts. They're pretty inexpensive, of $1.50 a piece. Some values can get a little more expensive than that, but it's a good choice and a safe path to go down. You've got your Panasonic metallized poly caps. They typically look like this. They're kind of brown in nature. They're very high quality. They have very common values. They come in either 450 or 630 volt values, and they're fairly inexpensive at about $2 a piece. I see a lot of audio techs using these, and I use a lot of them myself. If you wanted to step up just a little bit potentially, I believe the Solene Poly Fast Caps, they're very high quality. They come in in your common audio grades. They're 630 volt rated, and they're typically $3, $4, $5 a piece, depending upon the value here. And you guys have probably seen me use some of these in a lot of the gear I've worked on over time. And last but not least, even though these aren't new, they are very high quality, even if they're vintage, new old stock. And these are paper and oil caps. These could be things like your vitamin Qs. These could be things like your Russian paper and oils. I will tell you the common values are getting harder to find these days. There used to be tons out there surplus wise. They're getting much harder to find today. They come in a variety of voltages here, and they can range you anywhere from about $3 to $10 a piece. So they're getting on up there in price, but they do make an excellent sounding audio cap. And lastly, I want to come back around. There is forever ending debate on the sound of coupling capacitors in your amplifier. Oh, I put in these orange drops. They sounded better than the yellow poly caps. Oh, I replaced those with some vitamin Q paper and oil caps. Oh, they even sounded better than the orange drops. It is a large subjective debate, and we're not going to get into that today. What I'm going to say is that some people believe that different coupling caps have different tonal qualities to them, and then ultimately affect the overall sound of your amp. If you believe that, then you can pick the ones that you like best. Otherwise, I would recommend you could use about any of these to replace in your circuit, and they all sound fairly good. All right, let's jump over to the bench now. Okay, we've got this ICO HF85 that I'm in the middle of restoring, and realize, look at this. We've got 1, 2, 3, 4, 5, 6, 7, 8 coupling capacitors here that need to be replaced, as well as kind of a death cap over here of sorts that I'm going to replace as well. There's also a few electrolytics inside this unit that I'm going to replace, but that's not what today's video is really about. What it's really all about is what am I going to replace these capacitors here with. And if you'll notice, this is a 0.25 at 200 volt DC. And every one of these is 0.25, 0.25, 0.25, 0.25. And then we've got 4, and if you read this one, it's 0.1 microfarad at 400 volts. So we're going to figure out what we're going to use to replace these with. I will tell you that these are the old, as you can see here, just wax paper type capacitor. These are the worst of the worst. These are the ones that break down very easily and leak between one stage and the next stage and wreak off kind of havoc on your amplifier and your tubes themselves. So let's get busy replacing some of these. Alright, so I've gone in here and I've looked at what I've got. I've got 0.22 microfarad orange drops. I've got some 0.1 microfarad orange drops here at 600 volts. Could use both of those in here easily. One thing you'll note, these orange drops are fairly large in size relative to the counterparts here, what we could go with. These are 0.22 microfarad, 630 volts, and 0.1 microfarad, the 630 volts, the 150 Mallory M series. I think because the individual's not wanting to spend a ton on this amplifier and he's just wanting to get it working, I'm going to go in with the Mallory M series here, and I think it's going to work out great in this unit. I really don't think you'll tell much difference, if any at all, tonal wise between the Mallory 150s here. These are great caps. I use them in a lot of different gear restoration. Alright, what's the first step we're going to do? You're right, we're going to take a close-up picture or two from a few different angles of the device we're about to replace. That way if we get into it and we're like, oh gosh, you get called away and you have to come back later, you'll remember, oh, that was supposed to be a 0.25. We're going to replace it. So I am going to replace the 0.25s with 0.22s, and I've done that before in ICO HF85s, and I've checked the frequency response. We won't see a degradation there. And I'm going to replace the 0.1s with some 0.1 microfarads. All right, I do like to use PTFE wire cover here, and you can see I've slid it onto the lead of this capacitor. So as we're kind of dressing from the capacitor down to where we're going to solder it to, I like to use this to insulate the wires along the way. Okay, the way I like to do these is kind of one at a time, and I kind of like to just snip them out from wherever they're in the circuit. And pay close attention to where you snip it from, because you're going to have to put it right back. You'll notice that this capacitor does have a stripe on one end that in the older days they used to indicate that for the outer foil of the wrap of the capacitor, and then ultimately if you're replacing it with new ones that were marked, you could do the same. But it's not really as much a positive negative indicator as it is which is the outer foil versus the inner foil on the winding. And there is some belief system that says keeping the outer foil winding in the same direction as it came out can help reduce noise in the circuit. However, we're replacing it with the Maury 1Ms here that do not have a indicator on either end to show which is the outer foil winding or not, so it really doesn't matter, to be honest, in this case. I know that's a subjective debate, but for what we're doing here today, you can get your gear very up, running, and functional without worried about the inner or outer foil piece of it. All right, we're going to kind of put this down in here, measure off our wire sleeve, and go from there. And as you can see, we've now got our capacitor in here, a little bit of Teflon wire coating, and then we've got it soldered off and in its place. It's a pretty simple maneuver typically, not a lot to it here. Oops. Not a lot to it, and we're just going to keep moving through all the 0.1s here. Alright, something interesting here. This ICO was a kit that someone built way back in the day, and I want you to see this. I cut one side loose here of this coupling capacitor. It was connected over here, and I started bending it back out of the way to get to the other side, and look what I found. You can see down here at this pin socket right here, whoever built this originally never soldered the other end of this coupling capacitor. It, I guess I'll call it factory error by the original builder here, but yeah, that wire, it's been over. Just, you can see I'm wiggling it like crazy, was never soldered. So I'm wondering if this amp hasn't had problems since day one here because of that. Look at that, I pulled it right out. You can see it was never soldered. It was just bent over and crimped there. Okay, we've now replaced all four of these with the 0.1s, used lead dressing where we can. And that took 10-15 minutes, something like that, to do all four of those and to get them in there properly. Now we're going to move on to these 0.25s. Alright, as you can see now, we've replaced all the coupling caps in this unit. Still got a couple of electrolytics, but that's outside the scope of this video. I really just wanted to show you how to replace coupling caps. Like I say, main thing, I used some 6337 mg chemicals solder, and in this case it's 0.050 diameter. Just using a Heiko FX888D soldering iron. That's a great little unit for under $100. Normal little just wire snip type devices. Some needle nose pliers to help bend some wires with. And then I'm just using some Teflon wire coating, PTFE coating, and I'll put a link down below to where you can pick up some of this stuff at. It comes in a variety of colors, and usually a yard or two of it will last you a long time. So that's it for now, everybody. I hope you learned something about replacing coupling caps and why you should. Give you an example. These two right here are on the front end, and they're really designed in case whatever device you have plugged into this has some DC offset on it, keeps it from getting into this circuit. Each of these are kind of decoupling various stages from a DC standpoint, and ultimately will help extend and keep these tubes lifelong and keep them biased properly. So thanks for watching, everybody. Stay tuned. We'll bring you more soon.